let's step into this module. As we've already seen, the detect class takes inputs from stages 16, 19, and 22 of the feature pyramid network. These inputs form a list of 3 tensors with different shapes, each carrying rich feature representations at multiple scales. Without further ado, let's jump into the forward method of the detect class. The end-to-end flag is set to false, since this function performs the forward pass of the detect module specifically for version 10. So we will step over these and focus on the next section. This for loop requires quite a bit of unpacking because several critical operations are happening at once. Before diving into the implementation details, let's take a moment to first understand the purpose of the detect module. The detect head is responsible for both localizing objects and classifying them within each detection grid cell. It processes multi-scale feature maps using 2 convolutional branches. CV2, which refines spatial features for more precise bounding box predictions. CV3, which focuses on class confidence estimation using efficient depth-wise convolutions. To enhance localization accuracy, the module integrates depth-wise convolutions to reduce computation while preserving spatial details. It leverages the distribution focal loss approach to refine bounding box predictions, leading to better object localization. We will cover what this is in much more detail. Finally, the detect class fuses feature maps from different scales, applying convolutional refinements and loss-based optimization techniques to improve detection robustness across various object sizes. By efficiently combining these elements, it ensures high accuracy object detection with optimized performance. The detect class takes several input arguments, as shown here. The number of classes 80, since this model was trained on the COCO dataset, and the number of channels for each input tensor is 64, 128, and 256, respectively. I think it's important to cover the rest of the initialization arguments to fully understand what's happening under the hood. NL is 3, indicating that we have 3 detection layers. Regmax is 16, representing the maximum value for the distribution-based regression offsets used in DFL, something we'll explore shortly. No is 144. The comment suggests this represents the number of outputs per anchor, but since YOLO11 is an anchor-free algorithm, I prefer to think of it as the number of outputs per grid cell. This is technically the same, but better reflects the fact that YOLO11 no longer relies on anchors like previous versions. For example, YOLOv11 used 3 different anchors per grid cell. Strides are 8, 16, and 32, but we'll discuss these in more detail later. Finally, the variables C2 and C3, defined using the max formulas you see here, split the 144 outputs per grid cell into 64 for bounding box predictions and 80 for class confidence predictions. If this feels like a lot of information at once, don't worry, I get it. That's why I've prepared the Colab notebook, where you can take the time and walk through these steps and calculations in detail. The CV2 branch performs the following operations sequentially, while the CV3 branch, since the legacy flag is set to false, will process these other operations also sequentially. We could simply print the module to inspect its components, but instead, let's take a better approach and visualize the flow in a more structured way. Each detection head processes the feature map in 2 different branches. Let's break it down. First, we start with the input tensor from stage 16, which has a shape of 1 by 64 by 60 by 80, meaning we have 64 feature channels and a spatial size of 60 by 80. The CV2 branch, which you can see here, helps preserve spatial details, which is crucial for accurate bounding box localization. First, we have a 3 by 3 convolution, followed by another 3 by 3 convolution. These refine the spatial information while keeping the number of channels the same. Then, a final 1 by 1 convolution is applied, adjusting channel relationships without affecting spatial dimensions. Now let's look at the CV3 branch. The input is the same tensor from stage 16, but unlike CV2, this branch is designed to enhance class confidence estimation. Instead of standard convolutions, It starts with a depthwise separable convolution. This means each channel is convolved independently using a 3x3 kernel before applying a pointwise 1x1 convolution to mix channel information. At this point, the number of channels increases from 64 to 80. This process is repeated in a second block, where another depthwise convolution is applied, followed by a 1x1 convolution. Finally, one last 1x1 convolution produces an output shape of 1x80 by 60 by 80. Now that both branches have processed the input, the outputs are concatenated together. We can follow along with the code. First, we perform the convolution operations for the CV2 path. Next, we move on to the CV3 path operations. We start with a depthwise convolution, followed by a regular convolution, then another depthwise convolution, and finally, a regular convolution. This sequence produces the output that, as mentioned earlier, will be concatenated. With that, we've completed the processing for the first input to the detection head, index 0. However, there are still two more input tensors. We repeat the same operations for the second tensor, index 1, and we also visualize here the dimension changes at each step. Finally, we apply the same process to the third tensor, index 2. Visualizing the tensor shape changes at each step for those interested in the details. But what exactly are these inputs to the detection head? They are the feature maps. Here, I'm showing a sample of 8 feature maps that help the network determine both the location and type of objects. The detection head processes all 15x20 values across the 256 feature maps. For each of these 15x20 grid cells, it further refines the data through additional convolutions, ultimately producing 64 values for the bounding box and 80 values for the class types. You can also check the resources available in our Colab environment, where all the CV2 and CV3 steps for the 3 inputs are broken down in detail. Feel free to explore them if you're curious or have any questions. Now, moving forward in our code flow, we'll step over this part and dive into the _inference method inside the detect class. Here, we first extract the shape from X, index 0, which we then use to concatenate our 3 previously concatenated outputs into a unified tensor. This process is easier to visualize in our Colab environment. You can see how the 3 concatenated outputs from earlier are first reshaped here. And then at the bottom, you'll find the final X_cat tensor with a shape of 1 by 144 by 6300, preparing it for the next processing steps. Another way to visualize this is by first examining each individual tensor. Each grid cell prediction contains 144 values, 64 for bounding box predictions, and 80 for class probabilities. What we're doing here is flattening the 60x80, 30x40, and 15x20 tensors, as shown. Once each of these tensors is reshaped into this form, we concatenate them to obtain xcat. Next, we step into the make anchors method. As input arguments, we pass our earlier x tensors, not the concatenated xcat, but instead the original x0, x1, and x2 from before. Additionally, we provide the stride tensor, which contains the values 8, 16, and 32, as well as the grid cell offset value of 0.5. In YOLO11, anchors are dynamically generated based on the feature map sizes. The function makeAnchors is responsible for this process. It starts by initializing 2 lists, anchor points, which will store the XY positions of each anchor, and stride tensor, which will keep track of the corresponding stride values. Next, it retrieves the data type and device from the first feature map to ensure consistency across computations. Then, we calculate the anchor points for each feature level. Since this process is repeated for all 3 feature levels, we'll quickly step over the first 2 and focus more on the steps for the 15x20 feature map. Here, it extracts the feature map's height and width and constructs a grid of anchor points. This is done using torch arrange to create coordinate values for the X and Y axis, adding an offset of 0.5 to center the anchors within each grid cell. The function then uses torch mesh grid to generate a full grid of coordinates, stacks them into a tensor, and reshapes it into a list of anchor points. At the same time, it creates stride tensor, filling it with the corresponding stride for this feature map. Finally, all anchor points and strides are concatenated into two tensors. The result is a set of dynamically computed anchor locations, ensuring that each prediction is assigned to a specific grid cell at the correct spatial scale. This approach allows YOLO11 to generate anchors without relying on predefined anchor boxes, making it more flexible and adaptive to different image resolutions. If that felt a bit fast, let's take a closer look at the individual values by focusing again on this feature map level. Our feature map has a width x of 20, meaning it spans from 0 to 19. But with the 0.5 offset, it shifts to 0.5 through 19.5. Similarly, the height y is 15, meaning it spans from 0 to 14, or 0.5 through 14.5 with the offset. We then combine the x and y coordinates by stacking them and reshape them to obtain our xy anchor points. To visualize this, we can run a helper function to clearly see the anchor points we have just generated. Next, we generate a tensor filled with the stride value, ensuring it matches the shape of the specific feature map level. This mapping makes it easy to link each anchor point coordinate to its corresponding stride. And just for fun, we can run this for all feature map levels to see the full results. Finally, we transpose index 0 and 1, just as in the code, preparing for the next steps. We'll continue making our way through the code. We'll skip this step since we're not exporting and focus on the xcat split step. Regmax is a variable with a value of 16 that was set during initialization. If you recall, our xcat tensor has dimensions 1 by 144 by 6300. What we're doing here is splitting it into box and class tensors as we prepare to process each of these separately. Similarly, we can run these in our Colab as well to visualize it.